Hi students, welcome to our online class. Today I am going to explain a few important topics from the chapter Electrostatics. Chapter name Electrostatics. The topics I am going to discuss now are: first one, energy stored in a capacitor. The first topic is energy stored in a capacitor. Second, applications of a capacitor. Applications of a capacitor in some electronic circuits. And third, effect of dielectrics in capacitor. So these are the topics we are going to discuss now. The topics are energy stored in a capacitor, applications of capacitors, effect of dielectrics in capacitor. Right. First we go for energy stored in a capacitor. Right. Already you know that capacitor is a charge storage device. Capacitor is a charge storage device. That is, the capacitor is used to store electric charges. Capacitor is used to store electric charges. Capacitor charge storage device. Right. Actually, the capacitor is not only used to store electric charges, but also it stores energy. It stores energy. That is, energy also can be stored in the capacitor. So the capacitor is a charge storage device as well as energy storage device. Capacitor is a charge storage device and also energy storage device. Right. There are different types of capacitors like spherical capacitor, cylindrical capacitor and parallel plate capacitor. Spherical capacitor, cylindrical capacitors and parallel plate capacitor. So these are some different types of capacitors. Right. So among the three, the most commonly used capacitor is a parallel plate capacitor. So one of the form of a capacitor is parallel plate capacitor. So most of the electronic circuit has parallel plate capacitor. Right. Okay, here generally the parallel plate capacitor consists of two plates. The area of cross section of each plates is generally represented by A, and the separation between the two plates is D. Right. So there is a parallel plate capacitor. It consists of two metal plates. Okay, each of them has the same area of cross section. It is denoted by A, and the separation between the plates is denoted by D. Right. Suppose the medium in between the plates is air. Okay, air medium is there in between the plates. Right. Okay, suppose this capacitor is connected to a battery. What is battery? Battery is a source of potential difference or a source of voltage. Right. So this is positive terminal of the battery and this is a negative terminal. Right. So battery is connected across the two plates of the capacitor having air medium in between the plates, and distance between the plates is D, and the area of cross section of each plate is A. Right. Suppose if the battery is connected between the two plates of the capacitor, the positive terminal of the power supply, that is positive terminal of the battery, attracts the electrons from, suppose, the first plate of the capacitor. So, this is first plate of the capacitor and this is a second plate, right. So, here first plate is connected to positive terminal of the battery and the second plate is connected to negative terminal of the battery. When this battery is connected across the plates, the positive terminal of the power supply attracts the electron from the first plate, attracts the electrons from the first plate. So, the first plate acquire positive charge because it lost electron. So, that is why it becomes positively charged, right. Suppose let minus q be the total charge of the electrons attracted by the positive terminal of the power supply from the first plate of the capacitor, right. So, the total amount of charge attracted by the positive terminal of the battery is denoted by minus q, right. So, this charge is transferred to the second plate of the capacitor, When the battery is connected across the two plates of the capacitor, the positive terminal of the power supply attracts the electrons from the first plate. So, the first plate acquires charge, positive charge. The amount of charge attracted by the positive terminal of the power supply is minus q. Okay. This charge is transferred to the second plate of the capacitor, So, the second plate of the capacitor becomes negatively charged. So, generally in capacitor, one of the plate is always positive and another plate is always negative. The magnitude of the charges in both the plates are same. So, it is positive charge, it is a negative charge, but the magnitude of a positive charge and a negative charge in both plates of the capacitor is same. So, this is parallel plate capacitor or charged parallel plate capacitor, right. So, to transfer this much amount of energy from one plate of the capacitor to another plate of the capacitor, work has to be done, or work is must be done. So, to transfer the charge from one plate of the capacitor to another plate of the capacitor, work has to be done. Okay, this work is done by external agency. So, work done by the external agency to transfer the charge from one plate of the capacitor to another plate of the capacitor is stored as electrostatic potential energy in the capacitor. The name of the energy stored in the capacitor is electrostatic potential energy. Listen, when the battery is connected between the two plates of the capacitor, the power supply transfer the charge from one plate to another plate. So, work has to be done to transfer this charge from one plate to another plate. That work done is stored as electrostatic potential energy in the capacitor, right. Suppose let us consider a parallel plate capacitor, area of cross section A and separation between the plate is D, and this is connected to a battery which provide a potential difference of V across the plates. The power supply, that is a battery, provide a voltage of V across the plates, right. Suppose let dq be a small amount of charge, dq be the small amount of charge which is given to the capacitor, So, if you want to give the charge to the capacitor, work is must be done. Okay. So, here to give the small amount of energy to the capacitor, the amount of work done is very small. It is represented by dW. So, dW be the small amount of work done okay, by the work done by the external agency to give a small amount of charge, that is dq. It is given by dW is equal to V into dq. The amount of charge given to the capacitor is small. So, that is why the amount of work done by the external agency also small. It is given by the relation dW is equal to V into dq, right. We know that capacitance of the capacitor or capacitance is generally given by the formula C is equal to Q divided by V. C, the capacitance of a parallel plate capacitor, and Q the total amount of charge given to the capacitor, and V total potential difference between the two plates of the capacitor. C capacitance of the given capacitor, Q the total amount of charge given to the capacitor, and V potential difference across the two plates of the capacitor given by the battery, right. Therefore, V is equal to Q divided by C. Substitute V is equal to Q divided by C in this equation. Therefore, small work done to store the small amount of charge dQ in the capacitor is given by dW is equal to Q divided by C into dQ. dW is equal to Q divided by C into dQ, right. So, this equation gives a small amount of work done to store a small amount of charge, that is dQ, right. So, what is the total work done to store the total charge Q? So, simple, by integrating this small amount of work done, we can get what is the total amount of work done to store the total charge, that is Q. That is total work done is denoted by W, it is given by integration of dW, integration of dW. So, the difference between W and dW is that W the total amount of work done by the external agency to store the total amount of electric charge, that is Q, and dW a small amount of work done by the external agency to store a small amount of electric charge, that is dQ. So, total work done, how can you calculate or get total work done? By integrating this small work done. So, W is equal to integration of dW, or W is equal to integration of dW Q by C into dQ, Q divided by C into dQ. Right. For a given capacitor, its capacitance value is a constant. So, constant value we can't integrate, so take outside. Therefore, W is equal to 1 divided by C into integration of Q into dQ. So, here C capacitance of a given parallel plate capacitor. For a given capacitor, its capacitance value is a constant value we can't integrate. So, that is why it is take outside. So, W is equal to 1 divided by C into integration of Q into dQ, right. W is equal to 1 divided by C into integration of Q into dQ, Q power 1 plus 1 divided by 1 plus 1. So, W is equal to 1 divided by C into Q square divided by 2, or W is equal to Q square divided by 2C. W is equal to Q square divided by 2C, right. From this equation, C is equal to Q divided by V, therefore, Q is equal to C into V. Q is equal to C into V. Substitute to Q is equal to C into V here, then W is equal to CV the whole square divided by 2C, or C square V square divided by 2C. C cancel. So, therefore, W is equal to half C V square. So, the total amount of work done by the external agency to store the charge of Q in the capacitor is given by either W is equal to Q square divided by 2C, or W is equal to half CV square. W is equal to half CV square, right. So, this work done by the external agency is stored as, right, this work done is stored as electrostatic potential energy in the capacitor. Electrostatic potential energy in the capacitor. So, total work done by the external agency to store the total charge Q in the capacitor is stored as electrostatic potential energy in the capacitor. Electrostatic potential energy stored in the capacitor is denoted by capital U suffix E. It is given by either Q square divided by 2C or of CV square. So, electrostatic potential energy stored in the capacitor is given by the formula U suffix E is equal to Q square divided by 2C. Q the total charge stored in the capacitor, and C capacitance of the given capacitor, and V the potential difference across the two plates of the capacitor, potential difference across the two plates of the capacitor, right. Okay, so here from this equation it is clear that the electrostatic potential energy stored in the capacitor is directly proportional to square of the total charge in the capacitor. The electrostatic potential energy is directly proportional to square of the charge or total charge in the capacitor. And also electrostatic potential energy is inversely proportional to capacitance of the capacitor. Inversely proportional to capacitance of the capacitor. It means if the charge in the capacitor remains constant, then electrostatic potential energy in the capacitor is inversely proportional to capacitance. Inversely proportional to capacitance. In this equation, electrostatic potential energy is directly proportional to square of the voltage between the two plates of the capacitor. Electrostatic potential energy is directly proportional to square of the potential difference between the plates of the capacitor or the square of voltage between the plates of the capacitor. And also the electrostatic potential energy is directly proportional to capacitance. Here electrostatic potential energy inversely proportional to capacitance when if the charge is constant. If Q constant, then electrostatic potential energy is inversely proportional to capacitance. But here electrostatic potential energy is directly proportional to capacitance. Okay, in this case V is constant. If V constant, U is directly proportional to C. If Q constant, electrostatic potential energy is inversely proportional to capacitance. Right. The energy, electrostatic energy stored in the capacitor is given by the formula U suffix E is equal to Q square divided by 2C or of CV square, right. So, this energy is mostly stored where the electric field exists in the capacitor. The electrostatic energy is stored in the capacitor. Where the energy is stored? Okay, in the capacitor, where the electric field exists in the capacitor, okay, at the place only the energy is stored. So, it can be proved or this can be proved, right. For that, we know the formula for a capacitance of the air filled capacitor. C is equal to epsilon naught A divided by D. If the medium in between the plates of the capacitor is air, then the capacitance of the capacitor is given by the formula C is equal to epsilon naught A divided by D. There is a relationship between potential difference and electric field, that is E is equal to V divided by D. The relation between electric field and electric potential formula is there, that is E is equal to V divided by D, or V is equal to E into D. V is equal to E into D, right. Already I told the electrostatic energy is stored in the capacitor. That energy is stored where the electric field exists in the capacitor. Okay. So, to prove that, we consider these two formulas. One is C is equal to epsilon naught A divided by D. So, this formula refers the capacitance of a parallel plate capacitor if the medium between the plates of the capacitor is air. And the relation between electric field and electric potential is given by the formula E is equal to V divided by D, or this equation can also be written as V is equal to E into D, right. Now, substitute V is equal to ED and C is equal to epsilon naught A divided by D in this equation. Then electrostatic potential energy equation becomes of, instead of C, epsilon naught A divided by D, instead of V, ED. So, E d square of epsilon naught A divided by D, E square and D square, D cancel. So, that is equal to 1 by 2 epsilon naught E square A into D, A into D. A area of cross section of each plates of the capacitor, and D distance between the two plates of the capacitor, distance between the two plates of the capacitor. Here area of cross section and distance between the plates product gives the volume of the space between the plates of the capacitor, volume of space between the plates of the capacitor. Plates of the capacitor. Area of cross section of the plate is A and separation between the plate is D. Okay, product of area of cross section and the distance between the plate gives the volume of the space, between the plates of the capacitor, right. So, here this is the total volume of the space between the plates of the capacitor. The amount of electrostatic potential energy stored in the capacitor where its unit volume is called energy density of the capacitor. Energy density of the capacitor. The energy density of the capacitor is denoted by small u suffix E. Capital U suffix E, this is electrostatic potential energy in the capacitor, whereas small u suffix E, energy density of the capacitor. Energy density of the capacitor is nothing but total electrostatic potential energy for unit volume. Unit volume. Unit volume means 1 meter cube volume. Suppose if area of cross section of each plates of the capacitor is 1 meter square, and separation between the two plates of the capacitor is 1 meter. Okay, the product of these two value 1 meter cube. 1 meter cube is nothing but unit volume. So, electrostatic potential energy stored for unit volume of the space between the plates of the capacitor is nothing but energy density of the capacitor. So, energy density of the capacitor U suffix E is equal to UE of epsilon naught E square into AD of epsilon naught E square into AD volume A into D. AD cancel, therefore, U suffix E is equal to of epsilon naught E square. So, energy density of the capacitor is given by the formula of epsilon naught into E square. What is epsilon naught? Permittivity of a free space. Permittivity of free space. Free space. So, it is a constant value. The value of epsilon naught is 8.854 into 10 power minus 12 Coulomb square Newton inverse meter power minus 2. The value of epsilon naught, that is permittivity of free space, is 8.854 into 10 power minus 12 Coulomb square Newton inverse meter power minus 2. So, this is constant. So, energy density of the capacitor is directly proportional to square of the electric field between the plates. So, from this equation it is clear that the electrostatic energy is stored where the electric field is exist between the plates of the capacitor, or where the electric field is exist in the capacitor. Actually, the electric field is exist in between the plates of the capacitor. The electric field is always directed from positive plate to negative plate. So, the energy also stored in between the plates of the capacitor. The energy and the electric field always exist only in between the plates of the capacitor. So, electrostatic potential energy stored in the capacitor is given by U suffix E is equal to, or capital U suffix E is equal to Q square divided by 2C or of CV square. Electrostatic potential energy. Whereas, energy density of the capacitor is given by U suffix E is equal to of epsilon naught into E square. What is energy density? Total electrostatic potential energy of the capacitor for its unit volume of the space between the plates of the capacitor is nothing but energy density. It is given by the formula U suffix E is equal to of epsilon naught into E square. So, from this equation it is clear that energy is stored in the capacitor where the electric field is exist. Right. So, this is for about energy stored in the capacitor. Right, over. And next topic, applications of a capacitor. Capacitors have wide application. Mostly the capacitors are used in electronic circuits. Electronic circuits. Some of the applications of capacitor in the electronic circuits are given our book. Okay, capacitors have wide application. Some of the applications of a capacitor in the electronic circuits are listed out in our book. So, first application, the capacitor is used in digital camera. Capacitors is used in digital camera for the purpose of providing flashlight. For the purpose of providing flashlight. While we take a photograph, a flashlight coming from the camera or a flashlight coming out from the camera. The flashlight coming out from the camera is due to the discharge of a capacitor in the digital camera. Discharge of a capacitor in the digital camera. The name of the capacitor used in the digital camera is flash capacitor. Flash capacitor. So, capacitor, one of the important application of capacitor is it is used in digital camera. Okay, while we take a photograph, a flashlight coming from the camera, this is due to the discharge of the capacitor, discharge of a capacitor. The name of the capacitor used in the digital camera is flash capacitor, right. Second, the capacitor is used in a device called Ott Defibrillator. The capacitor is also used in the device called Ott Defibrillator. Okay, in order to recover the normal function of Ott. During cardiac arrest, a large amount of voltage is supplied to the chest of the patient. That electrical energy is given by the capacitor in the device called Ott Defibrillator. The amount of electrical energy supplied by the capacitor in this device is of the order of 2000 volts. Nearly 2000 voltage of electrical energy is supplied to chest of the patient in order to recover the normal functioning of Ott. So, this voltage is provided by one of the capacitor used in the device called Ott Defibrillator. Okay, and the capacitance of the capacitor used in this device is 175 microfarad. The amount of voltage or amount of the electrical energy supplied by the capacitor to the cardiac patient is 2000 volts, and the capacitance of the capacitor used in this device is of the order of 175 microfarad. So, this is another application of a capacitor, right. And third, the capacitor is used in the ignition system of automobile engine. It is used in the ignition system of automobile engine for the purpose of eliminate sparking. Whenever the automobile engine is started, a large amount of spark is produced inside the engine. To avoid the spark, the capacitor is used in the ignition system of automobile engine. Okay, it is used in automobile engine to eliminate spark, to eliminate sparking, right. And fourth, the capacitors is used to generate electromagnetic oscillation. It is used to generate electromagnetic oscillations. Right. Okay, there is a electronic device called LC oscillator. That LC oscillator is used to generate or used to produce electromagnetic oscillation. In the LC oscillator consists of a completely charged capacitor, and this capacitor is connected to a inductor like this. So, this arrangement is called LC circuit. If a capacitor of capacitance C and an inductor of inductance L are connected in parallel, okay, like this, then the circuit is called LC circuit. If the completely charged capacitor is connected to the inductor, okay, in the LC circuit, there is a electromagnetic oscillation sets up in this circuit. The electromagnetic oscillation is sets up in the circuit. So, the existence of electromagnetic oscillation produced in the circuit is due to the electrostatic energy stored in the capacitor is first converted into electromagnetic energy or magnetic energy in the capacitor, and once again the magnetic energy stored in the capacitor is converted into electrostatic potential energy in the capacitor. So, this repeated condition produce electromagnetic oscillation. So, to generate electromagnetic oscillation, definitely the capacitor must be used. So, this is also one of the application of capacitor. And now last one, the capacitor is used to reduce voltage fluctuation or power fluctuations in power supply. And already I told, most of the parallel plate capacitor is used in electronic circuit. So, one of the important electronic circuit is rectifier. So, rectifier is one of the electronic circuit. It is used to convert AC to DC. Rectifier is a electronic device which is used to convert AC to DC, that is alternating current or alternating voltage can be converted into direct current or a direct voltage by using an electronic circuit called rectifier. That is, so this is AC. When this AC supply is given to the rectifier, so this signal becomes like this. So, this is AC and this is DC. So, AC can be converted into DC by using an electronic device called rectifier, right. So, even though the AC is converted into DC, this DC is not pure, that is, it is not pure DC voltage, To get pure DC voltage, filter circuits are used. The rectifier circuit converts AC to DC, but the output voltage obtained from the rectifier is not pure form, not pure DC form. To get pure DC voltage, we can use a filter circuit. So, one of the filter circuit is capacitor filter. Capacitor filter is used to smoothen the fluctuations in the output voltage obtained from the rectifier. The output voltage from the rectifier is fluctuates. So, to smoothen this fluctuations in the output voltage of the rectifier, the filter circuits are used. So, one of the important filter circuit is capacitor filter. That means, by using capacitor or capacitor filter, we can reduce the voltage fluctuations in the power supply or voltage supply. So, these are important applications of capacitor. So, first application, the capacitor is used in digital camera to provide flashlight. Second, the capacitor is used in the device called Ott Defibrillator, because it is used to recover the normal functioning of heart. The amount of voltage given by the capacitor to the chest of the patient is 2000 voltage. The capacitance of the capacitor is 175 microfarad. And third one, capacitor is used in the ignition system of automobile engine to eliminate sparking. And fourth one, it is used to generate electromagnetic oscillation by using LC circuit. So, in the LC circuit there is a capacitor. When the completely charged capacitor is connected to the inductor, an oscillation is sets up in this capacitor. The name of the oscillation sets up in this circuit is called electromagnetic oscillation. So, without a capacitor we can't generate electromagnetic oscillation. And last one, the capacitor is used to reduce voltage fluctuations or power fluctuations in power transmission or in the power supply, right. So, these are important applications of capacitor. So, applications of capacitor over. And third one, effect of dielectrics in capacitor. Topic, effect of dielectric. Right. First, what is the dielectric? So, dielectrics are the insulating materials. Dielectric are the insulating material in which there are no free electrons to carry an electric current. There are no free electrons to carry an electric current. Right. The example for dielectrics: mica, glass, air and paper. So, these are best examples of dielectric. Best examples of dielectric. The best examples of dielectrics are mica, glass, air and paper. Air and paper, right. Okay, so already I told the dielectrics are nothing but insulating material. The dielectrics are nothing but insulating materials, right. All the insulators are not dielectric. All the insulators are not dielectric, but all the dielectrics are insulated. All the dielectrics are insulated. The main difference between insulator and dielectric material is that insulators does not transmit electrical effects. But dielectrics can transmit the electrical effects. Insulator does not transmit electrical effects, whereas dielectrics can transmit electrical effect. So, dielectric also insulated. The insulator which transmit the electrical effects are called dielectric. So, dielectric are the insulating material, but all the insulators are not dielectric, but all the dielectrics are insulated. The difference between insulators and dielectric is that insulator does not transmit electrical effect and dielectric can transmit the electrical effect. For example, let us consider a completely charged plate or charged plate, right. Suppose the medium on either side of the plates is air. Air is one of the dielectric material. Right. Now, another uncharged metal plate is brought near the charged plate. Negative charges are induced at one side of the plate, and equal amount of positive charges are induced on the other side. Okay. So, there is no physical contact between these two plates. Without physical contact, the negative charges and the positive charges are induced in this plate. So, this is due to the presence of dielectric material. So, air is one of the dielectric material. Because of the presence of a dielectric material, there is a electrical effect is transferred from one plate to another plate. Suppose there is a rubber. So, this is one of the insulator. So, rubber insulating material is introduced like this. Now, the same uncharged plate is brought near this charged plate. There is no electrical effect, that is, there is no induced charges in the uncharged conductor, because the rubber is a pure insulating material. It does not transmit the electrical effect. If the medium is either mica or glass or air or paper, it transmits the electrical effect. So, if the uncharged metal plate is brought near the charged metal plate, the positive charges and the negative charges are induced on either side. So, this is the main difference between insulators and dielectrics, right. So, clear? The dielectric is nothing but insulating material which it does not contains any free electrons in it. So, it does not allow the electric current to pass through it. The best example for dielectric materials are mica, glass, air and paper. Insulator does not transmit the electrical effects, whereas dielectric can transmit electrical effects. Once again, we consider a parallel plate capacitor. Parallel plate capacitor, and suppose the potential difference between the plates of the capacitor is V naught. The amount of a charge in the capacitor is suppose Q naught, right. Therefore, the capacitance of the given capacitor is given by C naught is equal to Q naught divided by V naught, right. Here the medium between the plates of the capacitor is air. Let Q naught be the amount of charge in the one of the plates of the capacitor, and V naught is the potential difference between the two plates of the capacitor. The medium between the plates of the capacitor is air. Now, the capacitance of this capacitor is given by C naught is equal to Q naught divided by V naught, because the capacitance of the capacitor is defined as the ratio of charge given to the capacitor to the potential difference between the two plates of the capacitor. So, capacitance C naught is equal to Q naught divided by V naught, right. Suppose if the air medium is replaced by another dielectric material like a mica or ebonite or glass like that, right. If the mica or glass, dielectric material is introduced between the plates of the capacitor, definitely the capacitance value will be changed. Capacitance change. Okay, if any one of the dielectric material is introduced between the plates of the capacitor, the capacitance value change, right. So, the capacitor, there are two different ways of inserting the dielectric material between the two plates of the capacitor. There are two ways or two different methods of inserting the dielectric material between the two plates of the capacitor. And first method, when capacitor is disconnected from the battery, Second, when capacitor is connected to the battery, So, dielectric material can be inserted between the two plates of the capacitor in two different ways. They are when capacitor is disconnected from the battery, and the second one is when capacitor is connected to the battery, right. First, when capacitor is disconnected from the battery, right. So, here this is a parallel plate capacitor. The area of each plates of the capacitor is A, and separation between the plates of the capacitor is D. Now, this capacitor is connected to a battery like this, right. So, this battery provide a potential difference of V naught, So, because of this potential difference, the capacitor gets charged. Suppose let Q naught be the amount of charge in the capacitor. Listen, A, area of each plates of the capacitor, and D, the separation between the two plates of the capacitor. Now, this capacitor plates are connected to a battery which provide a potential difference of V naught. So, due to the potential difference, the capacitor plates gets charged. The amount of charge in the capacitor is Q naught. Then the capacitance of this capacitor, suppose the medium in between the plate is air. The medium between the plates of the capacitor is air. Then the capacitance of air filled capacitor is denoted by C naught. It is given by Q naught divided by V naught. So, before the dielectric material other than air is introduced between the plates of the capacitor, its capacitance is given by C naught is equal to Q naught divided by V naught. C naught is equal to Q naught divided by V naught. And another one formula also there, that is epsilon naught A divided by D. C naught, the capacitance of air filled capacitor, it is given by Q naught divided by V naught. Q naught, the amount of charge in the capacitor, and V naught, the potential difference between the two plates of the capacitor. And another expression, epsilon naught A divided by D. Epsilon naught, permittivity of free space. Permittivity of free space refers to either air or vacuum. Air or vacuum. It means the medium between the two plates of the capacitor is air or vacuum, then the permittivity is denoted by epsilon naught. Here the medium is air, so that is why epsilon naught. And A, area of the plates of the capacitor, and D, distance between the plates of the capacitor. So, capacitance of air filled capacitor can be calculated by using the two formulas C naught is equal to Q naught divided by V naught, or otherwise epsilon naught A divided by D. Epsilon naught A divided by D. Right. Now, a dielectric material, suppose like mica, is introduced between the plates of the capacitor, right. Then the battery is disconnected. Battery is disconnected, right. Initially the capacitor is connected to the capacitor. It stores the charge of Q naught. Okay. After introducing the dielectric material, the battery is disconnected. The battery is disconnected, right. So, after disconnecting the battery, the amount of charge in the capacitor is remains Q naught, remains Q naught. Okay. And after introducing the dielectric material, the capacitance of the capacitor will be changed. Suppose it is denoted by C. It is given by Q naught divided by V. C is equal to Q naught divided by V. This is because if the dielectric material is introduced, then battery is disconnected. The potential difference between the two plates of the capacitor change, but the amount of charge in the each plate of the capacitor does not change. So, due to the change in potential difference, the capacitance of the parallel plate capacitor is changes. So, that is why the capacitance of dielectric filled capacitor without battery is given by C is equal to Q naught divided by V. C is equal to Q naught divided by V, or another formula epsilon A divided by D. Epsilon, permittivity of the medium. Permittivity of the medium. Epsilon naught, permittivity of free space. If the medium between the plates of the capacitor is air or vacuum, then the capacitance expression can be written as epsilon naught A divided by D. If the medium between the plates of the capacitor is other than air or vacuum, the capacitance is given by C is equal to epsilon A divided by D. Epsilon A divided by D. Epsilon is equal to epsilon naught into epsilon r. Epsilon is equal to epsilon naught into epsilon r. So, here epsilon r, relative permittivity of the medium, relative permittivity of the medium, or dielectric constant. Dielectric constant. So, product of a permittivity of a free space and the relative permittivity of the medium gives the permittivity of the medium, right. So, the capacitance of a dielectric filled capacitor can also be written as epsilon naught epsilon r A divided by D. Before the mica material is introduced between the plates of the capacitor, capacitance C naught is equal to epsilon naught A divided by D. After introducing the mica material in between the plates, its capacitance becomes C is equal to epsilon naught epsilon r A divided by D. Here epsilon naught A divided by D is equal to C naught, because C naught is equal to epsilon naught A divided by D. Therefore, C C is equal to epsilon r. Instead of epsilon naught A divided by D, we can write C naught. So, if the dielectric material is inserted between the plates of the capacitor, capacitance value increases. Capacitance value increases because the relative permittivity value is greater than 1 for the medium other than air or vacuum. Okay, because for air epsilon r value is equal to 1. For air, relative permittivity or a dielectric constant value is 1. Other than air, the relative permittivity or a dielectric constant is greater than 1. If the mica material is introduced between the plates of the capacitor, definitely the capacitance of the parallel plate capacitor value increases. Capacitance of the parallel plate capacitor value increases, right. And next, already I told, if there is no battery across the plates of the capacitor, so the charge in the capacitor remains constant. If the dielectric material is either introduced or not introduced, the charge in the capacitor remains constant. But after introducing the mica material, the capacitance of the parallel plate capacitor increases. So, C value increases. C increases after introducing mica material. What about the Q value? That is Q naught value, it remains same. Even the dielectric material is introduced and the battery is disconnected from it, the charge in the capacitor does not change. So, Q naught remains the same, right. Okay, here one more thing, when the dielectric material is introduced between the plates of the capacitor like this, if the mica material is introduced between the plate, so this is positive plate of the capacitor, this is negative plate. This is mica dielectric material. If the dielectric material is introduced between the plates, the dielectric material gets polarized. The dielectric material gets polarized. Okay, it means one end of the mica material acquires negatively charged and another end acquires positively charged. So, these two are the two plates of the parallel plate capacitor already which provide an electric field of E naught, which is directed from positive plate to negative plate. If the dielectric material is introduced between the plates, the dielectric material gets polarized. So, again at the time of polarization of a dielectric material, okay, one end of the dielectric material acquires a positive charge and another end acquires negatively charged. So, these charges are called induced charges. So, this mica material itself acts as a capacitor. Okay, mica material itself acts as a capacitor. So, which produces its own electric field. Suppose its electric field is denoted by EI. So, E naught, the electric field between the plates of the capacitor without dielectric material. If the dielectric material is introduced, which produces its own electric field, that is EI. This electric field due to the dielectric material is directed opposite to the direction of electric field E naught, So, the net electric field between the plates of the capacitor after introducing dielectric material is E, which is equal to E naught minus EA. E is equal to E naught minus EA. It means if the dielectric material is introduced between the plates of the capacitor, the electric field value decreases. Experimentally, it is given by the formula E is equal to E naught divided by epsilon naught. Okay, listen. The dielectric material is introduced between the parallel plate capacitor. After that, the battery is disconnected from it. The amount of charge in the capacitor does not change. Okay, and the capacitance of the capacitor value increases. The capacitance of the capacitor value increases. And third, the electric field between the plates of the capacitor is decreases. It is given by the formula E is equal to E naught divided by epsilon r. E is equal to E naught divided by epsilon r. Since epsilon r value is greater than 1, therefore, the electric field between the plates of the capacitor after introducing dielectric material is less than the electric field between the plates of the capacitor before dielectric introduced. So, it means the electric field value is decreases if the dielectric material is introduced between the plates. Electric field is introduced between the plates. So, electric field decreases. Electric field decreases, right. And next, we know the relationship between electric field and electric potential, that is E is equal to V divided by D. Before dielectric material introduced, the electric field is E naught and potential difference between the plates of the capacitor is V naught. After introducing the dielectric material, the electric field is V E and the potential difference is V and the distance between the plate is D. Therefore, V is equal to E into D. V is equal to E into D. Substitute E is equal to E naught divided by epsilon r here. Then potential difference between the plates of the capacitor after dielectric is introduced without battery is V. V is equal to E naught divided by epsilon r into D. V is equal to E naught into D divided by epsilon r. E naught into D is nothing but V naught. So, V naught divided by epsilon r. So, V naught, the potential difference between the plates of the capacitor before dielectric material introduced. V, the potential difference between the two plates of the same parallel plate capacitor after introducing the dielectric material. From this equation, it is clear that if the dielectric material is introduced, the potential difference between the parallel plate capacitor decreases. So, potential difference also decreases. Capacitance increases, charge in the capacitor remains the same, electric field decreases and potential difference also decreases. And next one, the electrostatic potential energy stored in the capacitor before the dielectric material introduced is given by of Q naught square divided by C naught. U naught is equal to of Q naught square divided by C naught. U naught, the electrostatic potential energy of the capacitor before dielectric material is introduced. So, amount of energy is U naught, which is given by of Q naught square divided by C naught. Q naught, the amount of charge in the capacitor before dielectric material is introduced, right. And C naught, the capacitance of the parallel plate capacitor before dielectric material is introduced, right. Now, the dielectric material is introduced between the plates of the capacitor. The electrostatic energy becomes U is equal to of Q naught square divided by C. U is equal to of Q naught square divided by C, because charge does not change if the dielectric material is introduced between the plate, but the capacitance value changes. The capacitance is given by C is equal to epsilon r into C naught. C is equal to epsilon r into C naught. Substitute C is equal to epsilon r into C naught here. Then U is equal to of Q naught square divided by epsilon r into C naught, right. Of Q naught square divided by C naught is equal to U naught. Therefore, U is equal to U naught divided by epsilon r. Since epsilon r value is greater than 1, therefore, U value is less than U naught. It means if the dielectric material is introduced between the plates of the capacitor, the energy value also decreases. So, capacitor without a battery, the dielectric material is introduced, capacitance value increases, charge remains the same, electric field between the plates decreases, potential difference between the plates decreases, and also energy also decreases. The electrostatic potential energy in the capacitor value also decreases, right. So, this is the effect of a dielectric in the capacitor.